Good morning. Last time we discussed the notion of characters of irreducible representations, the relation to the Fourier decomposition of class functions on a compact Lie group, and I indicated how this can be used for the group SU2 to show that the representations, the irreducible representations that we described, those representations pi n in the spaces of homogeneous polynomials of degree n in two variables, that those basically exhaust all the irreducible finite dimensional representations of SU2. And if you're interested in details, then please consult the lecture notes. Today we are going to look at the same problem again. So the classification of the equivalence classes of irreducible representations of SU2. And we are going to determine, this time we're going to determine these equivalence classes, or the classification. So the statement last time was that this is the set of the classes determined by the pi n, where n runs over the natural numbers, and pi n is a representation of SU2 in the homogeneous polynomials of degree n in two variables z1 and z2, so polynomial functions on C2. And today we will do this by using algebraic methods. So we are going to analyze what irreducible representations for the Lie algebra should be. So let's recall that if we have so suppose that pi, so let's do this in somewhat greater generality. So let G be say a connected Lie group. And suppose that we have a continuous finite dimensional representation of the group G. So V is a complex vector space and pi is a continuous homomorphism from G to the general linear group of V. This is a continuous homomorphism, and therefore it's automatically smooth, because continuous homomorphisms between Lie groups are smooth. And so that means that we can take its differential at the identity element, and we get a representation of the Lie algebra, pi star, which is a representation of the Lie algebra in the Lie algebra of this group, which is the algebra of endomorphisms of V, equipped with the commutator brackets. Now, recall that the space so V is a complex linear space. And therefore, the space of endomorphisms is also complex linear. But this means that pi star extends to the complexification of this Lie algebra. So the Lie algebra has a complexification, which is basically, this is as a vector space, this is the complexification of the vector space G. And the commutator brackets on GC is just the unique complex bilinear extension of those brackets. So there is a natural complexification of the Lie algebra. And then, so we have a real linear map from G to here, but since this is a complex linear space already, this map has a unique extension to a complex linear map here, and this will be a Lie algebra homomorphism. So we have the complexification of pi star, and this will now be a homomorphism of complex Lie algebras. So note that so pi star of C of an element x plus I y with x and y elements of the real Lie algebra is just defined as pi star x plus I pi star y. Okay. And now, of course, the question is, what can we say about the notions of invariant subspaces, irreducibility, equivalence, etc., in terms of this Lie algebra and its relation to the corresponding notions for the group? And so the first lemma in this context is the following. Let W be a linear subspace of V. So V is, as we described it here, linear subspace. Then W is G invariant if and only if W is invariant for the complexification of the Lie algebra. Well, in fact, did I assume that G is connected? I did. G is a connected Lie group. And of course, for the implication from right to left, one would expect that it's quite obvious that the requirement that G is connected is needed. I mean, this goes by the usual techniques. Making use of the connected component of the identity. I'll explain in a moment. Secondly, the representation pi is irreducible if and only if the corresponding, so this is the representation of the group, and this is the corresponding representation of the complexified Lie algebra if this representation is irreducible. Now let's recall, what is the notion of irreducibility? Well, that means that the only invariant subspaces are 0 or the full space. Now if we know A, then B is obvious, because A asserts that the invariant subspaces for G and for GC are the same. And that means that the notion of irreducibility is the same. So B follows from A. So let's concentrate on the proof of A. Well, we have a similar result for the real Lie algebra. So let's call this the left-hand side of the equivalence, and let's call this the right-hand side of the equivalence. Then the left-hand side is equivalent to the statement that W is, this is G invariant. I claim that this is true. So what is the reason for this? Well, from left to right it's a matter of differentiation, and from right to left it's a matter of exponentiation, and using that the group is connected, so that the exp of the Lie algebra generates the whole group. So this is by means of techniques that we have seen already. I'm not going to elaborate on this. So, but if we have this
equivalence, then the fact that W is G invariant automatically is equivalent to the statement that W is GC invariant. Because if we have an arbitrary element of GC, then it can be split in a real and an imaginary part. And if both the real and imaginary part leave W invariant, then of course the sum also leaves W invariant. So this is quite obvious. W is GC invariant. So basically it's using our old techniques combined with complex linear extension. Okay. Now, what I want to do is I want to reduce the problem of determining irreducible representations of the group to determining irreducible representations of the Lie algebra. And therefore it's good to have an equivalence of irreducibility of representations. So let's first concentrate on the space of equivariant maps between two representations. So this will be the next lemma. So let's V pi and W rho be two continuous finite dimensional representations of the group G. So G is connected. Then, first of all, if we look at the space of G intertwining linear maps from V to W, then this is the same as the space of GC intertwining linear maps from V to W. And secondly, V is equivalent to W as a G representation, so maybe I should say pi is equivalent to rho. So this is as a representation of G. This is equivalent to the statement that the corresponding representations of the complexified Lie algebra are isomorphic. So this is as representations of the complexified Lie algebra GC. Now again, once we have A, we have B, because this means precisely that there is an isomorphism from V to W, which is G equivariant. But such an isomorphism is also GC equivariant because of this equality, and the other way around. So if we have an equivalence here, we get an equivalence there. I mean, the equivalence, the map that realizes the equivalence here is the same map that realizes the equivalence here. Right? So A implies B is quite obvious. And for A, well, what we have to do is show that if we consider a map T from V to W, linear map, and now what we have to show is that this map is intertwining for the representation G, if and only if it is intertwining for the GC module structures. So must show that T is G equivariance is equivalent to T is GC equivariant. Okay, let's look at the implication from left to right, and then
I'll make a brief comment about the implication from right to left. So assume that T is G equivariant. So this means that for all elements of the group, we can first apply the representation pi of x, then apply t, and this is the same as first applying t and then applying rho of x. Right? This is a map from V to W, and so this is a map from V to W, and this is a map from V to V, and this is rho is from W to W. Now, if this is true, then it is true. It is in particular true for x is the exponential of an element of the Lie algebra. So then we get that T composed, and we could take a real parameter T if we like. And then what do we get? We get that by the commutative diagram for Lie group homomorphisms, pi of x becomes e to the t pi star of capital X. And this is equal to e to the t times rho star of capital X composed with t. And now it's a matter of differentiating with respect to t in t is 0 to get the intertwining statement for the Lie algebra. So, and this is because this expression depends linearly on this is linear in this endomorphism, because composition on the left with T is a linear map, and therefore we can, by using that the differential of this composition is just this linear composition, we can take the derivative here, and this gives us pi star of x equals rho star of x composed with t. Now if this is true, then of course this is also true for x of the form u plus iv. Oh, this is bad notation. Let's say y plus iz, where y and z are elements of G. Because T is a complex linear map. Right? And so this shows that T is GC equivariant. And we have established one direction of the equivalence. We have established the implication from left to right, and from right to left we apply the usual technique. First of all, if T is GC equivariant, then it clearly is equivariant for G, because G is contained in GC. But then the exponentials here are given in terms of power series, and we are in a finite dimensional situation where linear maps are continuous, and so commute with power series expansions, and we get the equivariant property. From here we get this equivariant property for all t and x, and that then by using the G is connected and the exponentials generate the group, we get the equivariance for the group G. Okay. Now, so if we want to, so now because of this equivalence of equivariance and equivalences of representations, we can reduce the statement about the classification of SU2 to the complexification of its Lie algebra. And the reason is that we do already have candidates for the classification of SU2 hats, and those candidates are these representations. So the idea now is that in order to show that these representations, we know already that these representations are irreducible, and in order to show that they exhaust, so they're also irreducible representations so by dilemmas, pi n star c, if you like, are irreducible representations of the complexification of the Lie algebra SU2. And to show that these exhaust the equivalence classes of the irreducible representations, it is sufficient to show that these exhaust the equivalence classes of irreducible representations of the Lie algebra. Right? Because if there would be more irreducible representations of the group, then there would also be more irreducible representations of the complexified Lie algebra. So it is sufficient to show that the representations, or rather their equivalence classes, exhaust all equivalence classes of irreducible, finite dimensional, irreducible representations of the complexification of SU2. Okay, so let's first now determine the complexification of SU2. So what is SU2? SU2 is a sub-Lie algebra of the Lie algebra of endomorphisms of C2. So this is the 2x2 matrices with complex entries, with the property that the matrix is Hermitian anti-symmetric. This reflects unitarity of the group, and then the S stands for that we take the intersection of the unitary group with the special linear group, and the special linear character is reflected by the condition that the trace derivative of the determinant should be 0. Okay. Now let us look at what happens. I mean, this is a complex linear space, and this is a real linear subspace. So let us look at what happens when we multiply this space with I, the imaginary unit, inside this space. Well, anti-symmetry is going to be replaced by symmetry. Because if we take the star of I, then basically we take the complex conjugate of I, which is minus I. So that compensates for this minus. So A star is A. And the trace, we're not talking about the complex trace, which is a complex linear functional on the space of all complex 2x2 matrices. And the complex trace is complex linear in A, so if the trace of A is 0, then the trace of IA is 0 as well.
so the condition that the trace is 0 is preserved. Right? But this shows that SU2 intersected with I times SU2 inside that bigger complex linear space is trivial. And that means that the complexification of SU2 is realized as a complex linear subspace here. And what is this complex linear subspace? Well, in fact, it's all of SL2C. So hence, the complexification of SU2 is SU2 direct sum I times SU2. And this consists of all complex 2 by 2 matrices of trace 0. And that's it. There is no additional condition on A. I mean, well, clearly, these are subspaces of what I've written down here. And if I have a matrix which has trace 0, then it can be split in a symmetric and anti-symmetric part. Such a matrix can always be written as A is a symmetric part and an anti-symmetric part. And if the trace of A is 0, then the trace of its conjugate is 0 as well. So this map is traceless and this one is traceless. And so that means that indeed the space of 2 by 2 complex matrices of trace 0 decomposes as the sum of SU2 and I times SU2. Right? So is this clear?
I don't know why you don't have any other conditions on the complexification of SU2, just a trace.
Well, because what we basically do is, so any matrix here can be split in two matrices, one of the matrices satisfying this condition, and the other one satisfying that condition. That is the point. We'll give an example in a moment. So, now SL2C has a particular basis which will be important to us, and in fact it is the particular properties of this basis they really form the reason, the motivation for passing to the complexified Lie algebra. So the claim is that SL2C as a vector space over the complex numbers is three-dimensional, and it is spanned by the following basis, consisting of H, X, and Y, where of course I should specify H. H is this real diagonal matrix of trace 0, and then for the other basis elements, we basically have the freedom to choose this entry and to choose that entry. So we could choose X is 0, 1, 0, 0, and we could choose Y is 0, 1, 0, 0. Now, so this matrix is already symmetric. So this one belongs to I as U2. This one is not symmetric, nor is it anti-symmetric. We can split it in a symmetric and an anti-symmetric part. How do we get the symmetric parts? Let's first get the anti-symmetric part. So this is by subtracting from X
the Hermitian conjugate of x. So this will be 1/2 times 0, 1, minus 1, 0. And then we are left with a 1/2 times, and now we'll get the symmetric part. Right? And now this is an element of SU2, and this is an element of I times SU2. And for y we have a similar formula. Does this make it clearer what's going on? Okay. Now the reason for preferring this basis of the complexification is that these elements have very nice commutation relations. And I can write them down by heart, which is quite rare for me to remember anything by heart. But it stresses the importance of remembering these relations by heart. So the bracket of h with x is 2x, brackets of h and y is minus 2y, and brackets of x and y is h. Now any pair of elements of a Lie algebra that satisfy these bracket relations is called, any such pair is called a standard SL2 triple. So the triple HXY is called standard SL2 triple. And more generally, what we will see later is that compact Lie algebras, or rather their complexifications, have many standard SL2 triples inside them. And this makes it possible to get a complete description of their representation theory. This is something that we will discuss later. But then, of course, it becomes quite clear that we first have to develop in detail the representation theory of SL2. And once we know that representation theory of SL2, then we can use that basic representation theory for the general compact Lie group situation by using all those SL2 triples inside the Lie algebra. That's the idea. Okay. Now, okay. So the first thing I'm going to do is I'm going to calculate the action of SL2C. So we have the representation pi n star c, representation of SL2C in the homogeneous polynomials of degree n in two variables. And now I want to calculate this representation. So let's first write down the formula for the infinitesimal representation. This is given by the ddt at t is 0. And then we can take the pi of e to the ta. Now if we want to apply this to a polynomial, then we take it this way. And let's calculate this in the variable z. Then this is equal to the ddt at t is 0 of p, and the representation was defined by taking the action of the inverse of this matrix on z, e to the minus ta on z. And now we have to differentiate this. And by using the chain rule, now this is complex differentiable, so we can take the complex derivative, the complex Jacobian, and then apply it to the derivative of this expression.
which is minus A applied to Z. So let's use the linearity and put the minus here. And now in particular I'm interested what this, first of all, so this result is true for P such a polynomial, and then for a matrix from SU2. But now recall that we had an extension of this infinitesimal representation to an infinitesimal representation of SL2C, the complexification of SU2, by using complex linearity with respect to A. Now if we look at this expression so the definition of this is by complex linearity, and for A in SU2 we have an expression of this sort, but this expression is complex linear in A. And the reason is that the derivative of this polynomial is given by a complex 2 by 2 matrix, and the derivative is really a complex linear map. So this expression is complex linear with respect to A as an element of the endomorphisms of C2. And therefore, this expression is actually, so this shows that pi n star, the complexification, and then of a general element of SL2C, well, why not denote this by A as well, is given by the same formula. So the same formula dpz applied to AZ. Now let's calculate what this means, for instance, for the basis elements of SL2C. So let's first take A equal to H is 1, 0, 0, minus 1, then AZ is Z1 minus C2. And that means that if we apply the derivative, so dp of Z is given by derivative with respect to the first variable in Z, and then the Jacobian matrix has a second entry, this one, and then we have to apply this to, well, really of course to a column vector, which is, and I'll abbreviate this as, and actually I'm interested in minus this applied to AZ, I'm sorry. Just in this particular, so it's really HZ is really equal to this, is, and then with a minus in front. So this is minus Z1, the derivative with respect to the first variable on P, plus Z2 times the derivative with respect to the second variable of P. And now let us look at the situation that we take A is X. So what is X? Z. So this is 0. I'm very bad at matrix multiplication, so let's write it out in full. So this is Z to 0. And so if we now apply the derivative of P to this, we get that pi n star C of X is given by Z2 times D1 applied to P is given by Z2 times D1 of P. And likewise, 3 well, I forgot the minus sign, I guess. We have a minus sign here. 3 pi n star c of y is also such a differential operator. Let's have a look here.
Minus z1 d2 of p, I guess.
Absolutely. It's interchanging the roles of z1 and z2. So I could have guessed that, I suppose. Thank you. But guessing in front of the blackboard is a bit difficult sometimes. Okay, so we get this. So now, but we do have a basis of our representation space. So we now know what the actions are, and maybe it's a good idea to repeat it here. So let's write it differently. On the space of homogeneous polynomials of degree n, we have that h behaves like, what is it? Minus z1 d1 plus z2 d2. X behaves like minus z2 d1, and y behaves like minus z1 d2. Now we have a basis. We have a basis consisting of the polynomials p0, p1 up to pn, where this is z1 to the n, z1 to the n minus 1 z2, and z2 to the n. So the general formula is pj is z1 to the n minus j times z2 to the j. Now let's look at what happens if we differentiate. Then this is a kind of this preserves the homogeneity. This preserves the degree in the variable z1, and this preserves the degree in the variable z2. So what we see is that h of pj is a certain scalar times pj. Now what is the scalar? Well, differentiating here is n minus j as a factor in front, with the minus is j minus n, to j minus n. Okay, what happens if we apply x to pj? Well, then something else happens. The degree in z1 is lowered by 1, and in z2 it's raised by 1. And so that means that x is a raising operator with respect to these indices. So this is this correct? No, it's a lowering operator with respect to these indices. Or did I?
J minus n p j plus 1.
J minus n pj plus 1. So I now realize that I have chosen the enumeration of the basis in such a way that x becomes a it becomes a raising operator for the weight structure. That's fine. Okay. Now y applied to pj is we do the same thing. So now we get minus j in front, and then p to the p times p of index j minus 1. And now clearly these formulas determine the representation pi n completely. Right? It's quite clear. We have written out the action of basis elements of SL2C on a basis of the representation space. So basically this gives us matrices for the action of h, the action of y, and the action of x, and the action of y. And so what we could now try to do is start with an arbitrary irreducible representation of SL2C and try to point out that it must have this structure. And this is exactly what we are going to do, but we are going to do it in a slightly different form. So I'm now going to concentrate on a arbitrary, so let V be an arbitrary irreducible SL2C module of finite dimensional irreducible SL2C module. And I'm going to reason about this module. And the first thing I'm going to do is I'm going to introduce, so note that here H diagonalizes over the basis formed by the PJs. And this is reason for introducing a generalized notion. So suppose that we have any complex number, then we define V sub lambda to be the space of vectors that behave like lambda under the action of H. Right, so this is a joint this is an eigenspace for the action of H on the module V, and the eigenvalue is lambda. Now, if this space is non-trivial, then lambda is called a weight of the representation. And capital lambda of V is obviously a finite set. It's the set of weights, or the set of eigenvalues of the action of H. Is the set of weights, and this is finite. By finite dimensionality of V. Okay, lemma. And this lemma, I think this is an appropriate lemma to finish the first half of this lecture with. This lemma expresses the raising and the lowering nature of the x and the y. So the lemma is that if we apply x to a weight space of weight lambda, then we will get a subspace of another weight space, and the new weight is determined by adding the 2 to the original weight lambda. And similarly, we have a formula of this type. Now the plus and the minus 2 come from the SL2 triple relations. I'll explain that. So I'll give the proof of A, and of course B is established in a similar fashion. Proof of A. Let V be an element of this weight space. Now I want to show that if I apply x to V, then it should be in this next weight space. So consider x applied to V and then apply H to it. And look what happens. Now I'm going to rewrite this as first applying H and then X, and I'll leave out the brackets. But then I have to compensate for this by a commutator. And this, I can do this because we have a module for the Lie algebra, and so that means that these are really the operators by which x acts on the module V, and by which h acts on the module V, and the commutator of these operators is the operator given by the Lie brackets. So this is the reason for this formula. Now, why am I interested in the right-hand side? Well, because I know that V behaves like the scalar lambda under H. So this is x applied to lambda V. And I know that there is a very nice commutation relation here. This is equal to 2x applied to V. Now, of course, this is x operates by a linear map, and so we really get lambda plus 2 times xv, and so this shows that xv belongs to the weight space of weight lambda plus 2. Okay, so I think this is a good moment to have a break. Let's have a break of exactly 15 minutes.